Hello, I'm José Alvarez. I'm Engineering Director for Video Technology at Xilinx. And today we'd like to talk to you about sensors, image processing systems, and embedded vision processing in general, and how FPGAs are a great solution for that space. First, let me start by outlining the general configuration of an imaging sensor. Imaging sensors are typically subsampled in a Bayer pattern, and this is actually a mosaic pattern that is composed of green, red, and blue sensing elements, each of them subsampled in a different way. You could see here from this diagram that the green components are actually subsampled twice as much as the red and the blue components. The idea being that you actually have more resolution from the green than of the blue. The point is to increase the perceived resolution of the sensor just by simply having color filters at each of the components, and then therefore get all of the photons impinging on the sensor. We're not going to talk about lenses, but we will talk just about sensors and the processing systems that are interfaced to them. The idea here is that from the single elements that are sensed, you produce RGB triplets components. So for instance, in this diagram, you have the original green component surrounded by the original blue and red. And the idea is to produce red components and blue components out of that one. And that is a process of interpolation. And so you could see here that from that original green, you got an R prime and a B prime, which are interpolated components. Similarly, for the blue sites, you essentially have the green neighbors and the red neighbors. And then you produce G, B, and R components. Again, the green and the red are interpolated in this case. And again, for the red actual samples, then you interpolate green and blue. Now let's talk about imaging sensors and the type of imaging sensors that you may get in the industry. This is a list. It's not a complete list, but it's a list of one of the most important things that you need to consider when interfacing to an imaging sensor. For instance, you have to consider the image sizes, frame rates, data widths, data formats, color spaces, and synchronizations, to name a few. For example, when it comes to image sizes, you may have images that are all the way from CIF resolutions to SD to HD, up to images nowadays of very, very large sensors, 12 megapixels and above. Typically, most sensors nowadays are in the range of 8 megapixels, so that is really a very good option for interfacing to image systems. When it comes to frame rates, then you can have anywhere as low as 15 frames per second to 60 frames per second or above, but typically these are the ranges that you see. Moving right along in the list, when it comes to data widths, then sensors can come in many, many, many different forms. You could have various bits per words, from 8, 10, 12, 14, and up to 16 bits per component, and that's really the bit depth. And also endianness. If your sensor is a parallel sensor, then endianness comes into play as to where the components are, and also the ordering of the components as well. It could be RGB, GBR, etc. When it comes to data formats, then you may have a number of things that come out of the sensor. The data can come either in parallel format, serial format, or as I was mentioning before, RGB, BGR, or GBR, depending on the type of sensor. Moving right along, on color spaces, most sensors are RGB sensors. However, there are sensors that come in other formats like CMY, etc. So all of those are available in the market. And then finally, you may want to consider a number of options when it comes to synchronization. For instance, blanking, active video, which are the parts of the sensor that actually contain picture elements. In many cases, sensors have areas that are not actual pixel elements, and those are used to do pre-processing of the sensor, sometimes noise reduction or changing the brightness dynamically, and also horizontal and vertical synchronization pulses as well. Moving on to imaging sensors, one example, for instance, on data rates is as follows. So let's say that you have an 8 megapixel sensor that produces frames at 60 frames per second. So you could see here from this diagram that very quickly your data rates escalate very, very fast. If you have 8 bits per sample on each of the sampling components, and these are the Bayer components that come out of the sensor, very quickly you have 384 gigabits per second data rates. You can see here when 12 megabits per sample, you will have 5.76 gigabits per second, and 16 bits per sample, you will get 707.68 gigabits per second. In the case of 12 bits per sample, packing comes into play, because you may want to pack the 12 bits into either contiguous words if the sensor interface is parallel, or you may want to pack them into 16 bits per sample as well. In that case, obviously the rate is higher. Now notice that these rates here are pertaining to the raw sensor, which means that once you convert them to RGB, you essentially have to triple the data rates that you see here. So now let's talk about image processing systems in the context of embedded vision systems. Here in this diagram, you see that we have a sensor, a display device, and a processing system in the middle. It's implemented in an FPGA. We're going to go over why FPGAs are a very good solution for these types of systems. On the left-hand side, you could see the sensor that can be in many, many configurations. It is typically sampled in the RGB Bayer domain. However, the interfaces could vary widely. The size of the sensor can vary. The frame rate of the sensor can vary. And also indicated here, the blanking can also vary, so that the amount of active pixels could vary from one sensor to the other one. The key thing to remember here is that one of the reasons that FPGAs are a very good solution for this is that they can actually decouple your problem, so that you have your sensor interface that can change depending on market conditions or even applications, and then your processing system as well. So both your sensor can change, so you decouple that part, and also your display can change. For instance, in the input part, your sensor can actually produce data that could be parallel in many configurations. The endianness can change in the parallel data as well. It could be serial configuration as well. It could be multiple bit serials or single bit serial. And the synchronization and interfaces can actually change, as well as the nature of the data as it's being transmitted from the sensor to your device. For instance, it could be in the LVDS format. All of this contributes to having FPGAs to be a very good solution. Now, the interfaces that you see here go directly into your system, and then you typically want to convert your Bayer subsample data into real RGB triplet data. And that you do by doing a color filter array processing. You can have an ISP, an image signal processing system, that uses internal BRAMs to save in memory configuration and also power as well, and then that data being processed internally by your system, and your system then could access external DRAM as well. The advantage of having a system like this is that you could actually vary the efficiency of your ISP depending on your application, and not only that, you could actually tailor the interface so that your processing system can actually detect objects, backgrounds, etc., and at the same time display it in a way that an operator can actually make decisions on the data. So notice that that could entail two different processing paths. One path that is optimized to the visual system so that the operator can make decisions on the data, and the other path optimized to your own processing, which means that it could actually detect objects more precisely. For instance, that data that goes to your processing could be just edges or colors or areas of the picture that are not necessarily very easy to detect by a human operator, but very good when you want to tailor your process so that you are effective in deriving information from your raw sensor data. On the other side, now you see that, again, we see that decoupling of your system and your display, and that decoupling comes because many times you need to display the data in a variety of ways. For instance, your display could be DVI-based display. That is parallel data RGB. It could be HDMI, more tailored to consumer systems, where your data could be not only RGB, but also YUV domain as well. It could be DisplayPort, very common in computer systems as well. And it can be changed dynamically because of the virtue of the programmability of the FPGA. Or it could be for broadcast systems where SDI, many medical systems use SDI connectors to your display. Now that you have your raw data into the system, you will want to convert the RGB subsample data and demosaic it into your RGB triplet components. For that, you use what we call an ISP system, an image signal processing system, that converts that data into something that can be used by the rest of your system. Typically, you do that by performing operations on the original data that could be two-dimensional operations. Two-dimensional operations require internal memory buffers. So those line buffers can actually be implemented using what we call BRAMs. And the BRAMs are a very convenient way to save you in the use of external memory, but also to save you power, because you don't have to actually send that data outside of your system itself, but actually do all of the processing internally. Let's talk a little bit about the image processing system inside the FPGA. Here we see that we have a sensor interface that connects to the outside world, typically the sensor with the many configurations. And internally here, we have what we call an iPipe, which converts your raw data from the sensor into something that can be used for further processing. This diagram only depicts the iPipe processing, meaning the conversion from the raw RGB domain to something that can be used by either internal processing, a vision system, for instance, not depicted here, or directly for display. So for the purposes of this diagram, you start with your raw data from the outside world. You may want to do some defective pixel correction, and then derive statistics information so that you could actually do white balance correction or others. From then, you do color filter array. At this point of the pipeline processing, you have RGB components. After having the RGB components, you may want to choose to do color correction matrix. This is where the white balance operations happen, and then gamma correction prior to display. At any point of the pipeline, you could actually draw data for your processing system. Finally, you can do a color correction, color space conversion that will allow you to go from the RGB domain to a YUV domain, perhaps for display. Notice that all of the individual IP components that are available from Xilinx can be controlled dynamically by a microprocessor. In this case, it's a microblaze that can not only control the individual IP, but also has the ability to control other external IP. These are part of the Xilinx IP infrastructure, and you could have an UART for serial control, Ethernet for connection to your network, or even USB. What we would like to emphasize is the flexibility that FPGAs provide you in building embedded vision systems. For instance, as indicated in this diagram, you have flexibility not only of interfacing to a number of sensors from the outside world, but also the flexibility of interfacing to displays or any other device that receives your data. You have the flexibility of instantiating different IP components that are provided through the Xilinx libraries, and the flexibility of controlling those components in various ways, even dynamically with a microprocessor control. You have the flexibility of implementing algorithms that can be tailored to your application, not only by instantiating components that are either optimized for speed or area, but also components that are optimized for bit widths and data formats, etc. In addition to that, the IP library provided by Xilinx allows you to instantiate additional components that are not related to vision processing. For instance, UART, Ethernet, or USB, all controlled internally through our microprocessor system, the microblaze. Today we've talked about why FPGAs are a great way to implement your embedded vision system. We've looked at a global template of how to implement those systems using an FPGA. The main item that we've discussed is the flexibility that is provided by FPGA in the interfaces, which allows you to use a variety of sensors in a variety of display. We've also talked about the ISP, converting your raw data into RGB data that can be processed by your intelligent vision system. However, we have not talked about the intelligent vision system itself today. In future installments of this series, we will be concentrating on the intelligent video processing and ways for you to implement this very conveniently using FPGAs. Thank you.